Okay, good morning. Yeah, I'm going to stay on the subject of sulfur, but we're going to shift the focus slightly to think about the role of sulfur and metals in active volcanic degassing, particularly in basaltic systems. This is work that I've been doing with Marie Edmonds, Tamsin Mather, and Margaret Hartley at Manchester. So we're all well aware that volcanoes have an important role to play in the geochemical cycling of sulfur and metals. They act as conduits, transporting these elements from the upper mantle either into ore deposits or directly outgassed into the atmosphere, where they can have a variety of implications for climate, for geochemical cycling, regional air quality, and also biological productivity. But there's still many gaps in our knowledge of exactly how these elements are processed by volcanic systems, particularly up in the shallow volcanic systems of active basaltic volcanoes. So you saw this, this was on Marie's poster yesterday and also in Tamsin's talk. This is a compilation looking at metal emissions from active basaltic systems. And we're still lacking quite a lot of data for this, but a few patterns are beginning to come out of this, particularly regarding the distinctive metal fingerprints between arc systems versus more reduced ocean island basalts. So in blue, we've got the arc volcanoes, and in red, the ocean islands, Kilauea, Holuhraun. Now, a number of trends are popping out. Overall, the ocean island basalts, the flux of metals is noticeably lower. Halogen-poor systems, the flux is overall reduced. However, there's a certain number of enrichments and depletions that appear characteristic of both Kilauea and Holuhraun and are suggesting of some general process that is fractionating in these metals. So this is something that I'm going to explore in this talk. Now, ocean island basalts, most of the sulfur is in the form of the 2-. It's in the reduced phase. So sulfide saturation, is going to be an important player in governing how these sulfur and metals are processed through the system. Now, in a number of ocean island basalts and morb, we see sulfide globules preserved in the erupted tephra, the ash and bombs. So this is indicating that at some stage we have reached sulfide saturation. Now, take an example, the Grímsvötn eruption in Iceland in 2011. It's been estimated that based on a discrepancy between how much sulfur would be expected to have been degassed based on petrological approaches versus satellite measurements, the discrepancy, and they attribute that to storage of sulfur, up to 50% of the sulfur retained in sulfides. However, the opposite could also be true. If you have shallow breakdown of sulfides, this could feed the gas plume in sulfur and metals. So we want to understand more about the conditions under which sulfide could act as a source or sink for these elements. So we don't have just a two-phase system between the melt and the vapor. We actually have to think about the three-way exchange between melt, sulfide liquid, and vapor. So I'm going to be focusing on the Holuhraun eruption. This was a basaltic fissure eruption in Iceland. It lasted around 6 months, from August 2014 to February 2015. This is quite a busy cartoon, so just focus on, it was a lateral dike intrusion, a lateral magma intrusion from the Bardarbunga central volcano. The dike was well imaged seismically at around 5 kilometers depth before it surfaced at the Holuhraun lava field. The eruption was remarkably sulfur-rich. It released up to 11 teragrams of SO2 over the course of the eruption. And put that in context, that's around 3 times the amount of SO2 released anthropogenically by Europe in the same time. So we analysed samples from the beginning, middle, and end of this eruption over the 6 months. And this was all rapidly quenched tephra, glassy tephra. All the samples were sulfide bearing. We found them in a variety of locations within our samples. Around 20% were as inclusions within mineral phases, either as melt inclusions, silicate melt inclusions, direct sulfide liquid inclusions. Around 30% were associated with microphenocrysts, mostly nestled within embayments. Around a quarter were directly adjacent to bubbles, actually in contact with the bubble wall. And then the final quarter was loose in the matrix glass. Some of the highest concentrations of these sulfide globules were found in association with half millimetre, millimetre sized glomerocrysts, which you can see can be absolutely raspberry covered in them. So clearly this is telling us that the magma was at or fluctuated near sulfide saturation for much of olivine plagioclase CPX crystallization. So straight away something we wanted to think about was, could the magma be assimilating sulfide-bearing cumulate crystal mush, particularly through the dike transport path? However, I don't think this is the case. The glomerocrysts, they tend to show a subophytic texture, which is not really what we'd expect for cumulates. And if we look at the mineral chemistry, particularly at plagioclase, its content is what's been calculated by Halldórsson et al. To be in equilibrium with the erupted matrix glass. So they seem to be formed by primary fraction crystallization. So what I showed you has been the 2D perspective. But we wanted to delve a little bit deeper and look at what these samples look like in 3D to explore the textural relationships between our sulfides, bubbles, crystals. So in a project led by Margaret Hartley, we went to the diamond light source, synchrotron, and using phase contrast imaging have separated out these three phases. This is still work in progress, and anyone who's worked on tomography data knows that this is going to be quite a long, protracted experience. But our preliminary observations are supporting what we see in 2D regarding the textural associations, many of which are located with these glomerocrysts. Interestingly, if we look at the size distribution of the sulfide, the size distribution we get from stereologically corrected 2D images compares extremely well to what we measure directly in 3D. So that gives hope to the stereological correction. But overall, we see a distinct mode between 12 to 17 micron diameter of these sulfides. But they extend from less than a micron up to maximum 40, 50 microns. If we look in a little bit more detail about the sulfides themselves, we see that most of them are intergrowths of two domains. So the overall shape suggests that they were liquid globules, but they've since undergone crystallization into our monosulfide solid solution, our iron-nickel-rich phase, and our intermediate solid solution, which is copper-rich. And I've divided them into 5 main component groups. Groups 1 to 4 are basically defined on the basis of how coarse the intergrowths are, from almost homogeneous monosulfide solid solution to discrete domains of the different sulfide minerals. And the change from 1 to 4 correlates very nicely with globule size. And this has been documented from Morb and attributed to differences in the degree of undercooling and rapidity of crystallization. However, type 5 is those sulfides noticeably breaking down. Now, these show no association with size necessarily. They're typically very sulfur and copper poor, iron rich. So they seem to be actively breaking down into iron oxides, iron titanium oxides. If we look at the temporal evolution between our 3 samples from beginning, middle, and end, overall the proportions of groups 1 to 4 remain approximately similar relative to each other. The big change comes in the proportion breaking down. So this is a very tiny proportion in our sample from the opening phase of the eruption. But after that, the colours haven't come out great there. About 50% of the later 2 samples, the sulfides are breaking down. This is a noticeable difference. If we look in more detail about this particular globule, this is one of my favourites. This is an EDS map here showing the different phases present in the globule. If the stars represent microprobe points, and these are plotted on this graph here. So we have pyrrhotite present, we have something on the way towards pentlandite, chalcopyrite, and something up as extreme as near bornite. So clearly, if we want to reconstruct the original sulfide liquid composition, it's not enough just to take single analysis points. So to reconstruct the sulfide liquid composition, we measured the compositions of our MSS and ISS domains, and then used a weighted average based on image analysis of our 2D sulfides. And what we see is actually the bulk composition of the sulfide liquid really doesn't change appreciably through the eruption. we come out around 47 weight percent iron, 34 weight percent sulfur, 17 weight percent copper, very rich, and 2 weight percent nickel. And this is in equilibrium with our monosulfide solid solution composition at around 1050 degrees C. So we suggest that's the temperature at which our sulfide liquid started crystallizing. Okay, so if we take our Holuhraun malt and fractionally crystallize it, we gradually increase our sulfur concentration here. This here is the range of melt inclusion compositions calculated by Margaret Hartley. And we see that our maximum melt inclusions corrected for post-entrapment crystallization are around 1600 ppm sulfur, or around 40% fractional crystallization. If we superimpose the sulfur content at sulfide saturation model from Lee and Ripley, we see that actually the magma should become sulfide saturated at very low degrees of crystallization, around 10% or just over. But something I want to look at is exploring the various different models that now exist for sulfur content at sulfide saturation. As now many include the iron effect and nickel effect on sulfide saturation. If we look at our melt inclusion data as a function of iron, we see that the melt inclusions in grey here, they lie just below, but parallel the Morb array. So the sulfur content in the melt inclusions appears to have a systematic relationship with iron, which strongly suggests that they are sulfide saturated, where the sulfur carrying capacity of the melt is buffered by the increasing iron content during fractional crystallization. But here, this is where we have the onset of degassing, and straight away you get a rapid drop in sulfur as it's degassed to the vapor phase, down to the matrix glass compositions around 400 to 500 ppm sulfur. Now, shown in blue here are profiles measured away from sulfide globules, shown here. So we're getting concentration gradients in sulfur away from globules, particularly those associated near crystals. So something we want to explore is whether we see similar concentration gradients in trace metals, but this is going to be a lot more challenging analytically. Okay, so whether sulfides act as a source or a sink for sulfur and metals is going to be critically dependent on the relative timings of vapor and sulfide saturation. So in ocean island basalts, they saturate in CO2 mid-crustal depths, but this is not particularly a good carrier for sulfur and metals. Water and sulfur only begin to exsolve very shallowly in these compositions, mostly in the top kilometre. You can see here it's a dramatic but very late stage drop-off. So we wonder whether the onset of this late stage main phase of vapour saturation causes destabilisation of our sulfide globules. They oxidise and resorb, releasing their sulfur and metal load into the vapour phase. We've got textual evidence of this. We see that those globules that are associated with bubbles show they're the ones breaking down. They're very iron-rich, sulfur, copper poor, and yet those in the matrix glass are typically a lot more happy. So potentially they're releasing the sulfur and metals directly into the vapour phase. So could sulfide breakdown supply sulfur and metals to the gas phase? That is the big question. And you saw this figure in Tamsin's talk yesterday. You can see that the ocean island basalts, the volatilities of the metals, they largely mirror the sulfide liquid silicate melt partition coefficients, not the silicate melt fluid partitioning, suggesting that we need more data, that the gas phase is being fed by congruent dissolution of sulfides. And this has been suggested based on similarities in metal ratios at other volcanoes between the gases and the sulfide. So even a small mass fraction of sulfide, could contribute a significant proportion of sulfur metals to the gas phase. It represents a concentrated reservoir. So by mass balance, if we even had a 0.1 mass fraction, 0.1% mass fraction of sulfide, this could contribute around 25 to 30% sulfur to the plume. If this increases to 0.5 weight percent sulfide, we could increase this contribution to around 50 to 60%. And this effect would be amplified for metals such as potentially copper, as relatively low volatilities from the silicate melt, but a very enriched reservoir in the sulfide. So something we want to really constrain is what is the typical mass fraction of sulfide present in these systems at depths relevant to volcanic degassing. So just to bring this all together, again, you saw this diagram or some variant of yesterday. We think that sulfide saturation is an important control on sulfur and metal systematics in basaltic systems, particularly reduced basaltic systems. We think that late-stage vapor saturation could trigger sulfide breakdown, where they release their sulfur and metal load directly into the vapor phase, enriching the gas plume. An important thing I want to emphasize here, though, is what we see in the erupted pyroclast is what's left. It's the residual. We're seeing the post-degassing textures, signatures. So potentially we're only seeing a tiny fraction of what was once there. It's potentially all gone into the gas phase. So something we want to look at continuously, and I know other people in the room are looking at this, is using trace metals in melt inclusions and glasses as cryptic indicators of sulfide saturation and evolution to combine with what we see texturally. And our systems in ocean islands are down at this end of the diagram, where potentially we're enriching our volcanic gases and chalcophiles. But globally, the distinctive metal fingerprints that I showed earlier are likely to be controlled by variances in the redox and water content between the different tectonic settings. So I will leave it there, and I'll take any questions. Thank you.
Time for a couple of questions. John?
You sure the gas is SO2 that's coming off and not H2S?
Yes, most of the gas is in the SO2 form. I don't have the number of the proportions, but H2S in these active systems that with a relatively little hydrothermal contribution is minor.
Right, so you've got a missing part of a redox reaction. So as you start to degas and you're taking sulfur out of the melt and putting it as SO2 into the gas, then in order to maintain sulfide saturation in the melt, you dissolve the sulfide. But that's a sulfide. Something must be getting... there must be a corresponding reduction. So you should see the ferric-ferrous ratio change as this takes place, because it's dissolving as sulfide, but it's exsolving as SO2.
So something's happening in...
Yeah, so you should be able to see that. I'm sure you would see it, but there must be some corresponding oxidation.
Yeah, no, that's something to look for. Thank you.
Okay.
Yeah, that's amazing. The difference between the little sulfide gobs that aren't looking all weird and those that are is what? In other words, you had some that are, what did you use the word, decomposing, or they're just filthy looking things, and some that still look lovely.
Yeah.
Was there a difference between them to start with? Like those messy type 5 things?
What I think is that they all began like this, and this is them in the active process of breaking down and resorbing into the...
So why did they go crook and the other ones didn't?
So they're the ones often next to the bubbles. So our idea is that those in contact with the vapor phase, they're the ones oxidizing and resorbing, whereas the ones loose in the matrix glass are more looking happy like this. Does that make sense?
Yeah, so the other thing I was going to wonder is like in komatiite flows, there's just heaps of sulfides that are happy as Larry in there. Why? Is it because they're so oxidized or hydrous or something else that they're such a mess?
The ones that are breaking down here. So it's not particularly a hydrous magma. It's very low water content, actually. So I think that's not the reason. I mean, almost more surprising to me is why are any happy in the first place. Technically, I don't really think there should be any left. Something that suggests to me with the sulfur concentration gradients is that actually the ones that we're seeing, they're actually perturbed almost metastably, and they should really have been all breaking down into this space. So I think I'm almost surprised the other way.
So the amazing trend you have where you have gold and stuff that's going like crazy off into the gas, that cool plot you have, could you show that again? Yeah, that one.
This one here.
That's the orange trend there, that's just measurements of
Yes.
gases?
So these are filter pack measurements from Holuhraun in Iceland and Kilauea, Hawaii, just with the volatilities of the different metal species.
What do you mean volatilities? They're measured in the gas?
Yeah, in the gas phase, the proportion of the metal that was present in the melt that's entered the gas phase.
Wow.
Is that a mass balance problem, or do you just measure the ratio, concentration ratio, or what?
Measurements between the concentration in the magma and the concentration that we measure in the plume.
So it's a partition.
A variance of.
I think we'll have to stop there. You guys are welcome to ask Emma questions at the coffee break. So thanks again.